So then welcome to the second lecture in computer algebra in the summer term 2025. So today we are going to use computer algebra a lot, but the subject of today is actually not so much about what computer algebra is and how it works, but about some physics and mathematics that we can use to actually study interesting problems in a very straightforward way. And this is done here through the Hamiltonian principle, which is equivalent to Newtonian dynamics in principle, but okay, it's a little bit more than that, but it gives us, from a computational perspective, a more straightforward approach to actually study large systems. Yeah. So in principle, you can, I mean, the mechanics guys in our department, they are very fond of Newtonian mechanics, and you can solve all the problems in civil engineering with Newtonian mechanics, but you can also do this with Hamiltonian mechanics, and this is actually easier to automate to do it in an automatic way because it's a more straightforward approach. So, and on top of this, what we do from now on is, this is not using PowerPoint or something similar, but Mathematica has a presentation modus, where you can do presentations in Mathematica. I don't think this is a very advanced presentation thing, but I think if you, when you do a lecture on Mathematica, then somehow you are supposed to use this. I mean, the advantage is that you can make the changes, trying out things during the lecture without changing the software. Okay, so here let's go on and see whether what is our principle that we want to use in order to study some mechanical systems. So we have to start with some definitions. So what we actually consider a system, and in physics now we could say that a mechanical system is made up of particles. So very, very down there would be particles, but we can generalize this a little bit later, as we'll see. So we say there would be n particles, and these particles are not completely free, but they are constraints. So say there are m constraints. So what would be a constraint? Say you have what is it? You have some oxygen or nitrogen atoms floating around in this room, So now each of them can be anywhere here in this room, however, and have any position and any velocity, However, this is not completely true because these things always come in pairs of two, right? So then this means that always two of them are constrained to stay close together, right? So because they are bound together. So there are some constraints, and these number of constraints, these are conditioned with m. So then these particles, because we are in three-dimensional space, they would have 3n minus m. So the constraints take away 1 degree of freedom each. Yeah? So we have 3n minus m degrees of freedom. And by degrees of freedom, we mean their position. Yeah, and in addition to their position, yeah, so we call this now generalized coordinates. Yeah, so because we are just we're just dealing. So this was the wrong button. We are just this was the wrong button again. What happens? Okay, so we'll define these things in a different later in different ways, but you can have different coordinate systems, obviously, yeah? Different ways to describe your coordinates. So we just say the number of coordinates that we have is 3n minus m, and we call these generalized coordinates qk. So because k is the index, so where we count them, right? And for each position, we also have a velocity, so the change of this position in time. Right, so then we have this accounts here for this time derivative, and by the way, you can write time derivatives in Mathematica like this. Yeah, so you would have qk is a function of t. Yeah, so this is indicated here, and you can write this. When I go down here, yeah, so you can. The way you do it in Mathematica is you press escape, yeah, and then this is a partial derivative, so it's called PD, yeah, partial derivative. You press escape again. It's a very archaic, typing system. So what you can then do is control. What is this? Control. This, I don't know, these underline thing, control underline, yeah. So here you can put a t, and now you will have, for example, a function. Okay, I don't know whether this is a good idea to call it like this. So if this is a function of t, so this, well, yeah, it takes this derivative. For example, if it's a function of x, then then it's not, yeah, obviously. If x, so and then you can go on x could be a function of t, so then you'll have this behavior, yeah. So actually, you see, I was saying we are not. Okay, I put a little bit of Mathematica stuff inside here, yeah? But actually we want to understand this Hamiltonian principle first. So the constraints that we are considering here are so-called holonomic constraints, and holonomic constraints are of the kind that depend only on the position and the time. Meaning the constraint does not depend on the velocity. Yeah? So velocity, so there's no explicit dependence on velocity for the constraint, only the position and the time. Then it's considered to be holonomic. Okay, and then we define the Lagrangian. So this is this L here, which we can also write as, you see, we can have script SC L, yeah, SC capital L, and this would give us this, this letter, yeah. But you don't need to use these letters, obviously. Okay, so this is now, you see, this is not a definition. I'm just, I'm not defining L, but this is the equation, yeah. So because I'm not going to use this, I'm just wanting to display what I just want to talk about it. I'm using this as a presentation tool here, yeah. So this L is the difference this Lagrangian, as we call it, L, is the difference between the kinetic energy and the potential energy. Yeah? So this is how we define this. There is some nuance to this, actually, that now, if we had a physics lecture, then, the physics professor would kind of bash me a little bit about this, because there's actually something, a co-energy, but this is the sufficient way to understand this for this lecture. So I'm simplifying this for engineering purposes. Yeah. So if you are interested, so don't go out the rest of your life and say your professor told you this is this, and and this is now for our purpose. Yeah. Okay. So, and now the interesting thing is that we want to describe the dynamics of such systems, and this goes through the principle of least action. And this is an axiom, and it is something that is kind of, I would claim it's kind of difficult to understand. I don't know whether it's difficult to understand. Usually people don't attempt to understand it, because one position, and this is also what I have been told, is this is a basic principle of physics that cannot be. There are equivalent principles that you could translate it, but actually it is a starting point. Yeah, so it's the basis that you have to accept, in a sense. Yeah, so you can say this is what we observe in nature. Yeah, so and now so the principle is that the trajectory in the phase space. So the phase space is the state, is giving us the state of the system, and the state of the system is has the dimensions of the coordinates plus the velocities. Yeah. So the system. This is not just like a picture where you see some particle in a certain position, but also it has a velocity. Yeah, this is also part of its state. Yeah. So and now it will have a state at one time instance, and it will have a state in another time instance, and the trajectory is all the states that it will have in between, going from one to the other, right? And this integrating the Lagrangian from one time instance to another time instance, this gives you something that we call the action. Yeah? And so integrating all of them, the entire sum over all the particles that we have, all the kinetic energies and minus the potential energies, and then there is, in this action integral, is something that is here. We'll talk about this a little bit later, and this is kind of an annoyance. This is there's some non-conservative energy, and this non-conservative energy is what we call dissipation. And this actually does not really belong here. This is another simplification for the purpose of being engineers. Yeah? So in engineering, we don't cover all of our energies like the entire universe would do, but we say there is some dissipation, so some leakage of energy out to the environment, if you will. Yeah? Like something turns into heat and then we don't care about it anymore. Yeah? If you look at all the atoms, and so heat is basically it's kinetic potential energy distribution. Yeah. So if you look at everything and you say, okay, I don't care, I'm not considering dissipation, I'm covering all the energies of all the particles moving around, then you don't need this. Yeah? So you enter this for the simplification of being an engineer. Yeah? Get this stuff out. Okay? So in principle, this works without this. So now so this thing is supposed to give us the path that is actually taken, and this is again, I mean, you could take the position that this cannot be explained, but this is simply an axiom of nature, that the action integral, so the path that is taken, minimizes or maximizes. This is that's in principle unclear. So depending on the definition, yeah, whether it's going this way, is taking it in an extremum. So the least action. So the way you can potentially, I mean, everything that I'm going to say is wrong. That I could say as an explanation would be wrong. But you could try to understand this in a little bit the way that this integral over the Lagrangian gives you, well, let's say the Lagrangian is getting off its center when there is more kinetic energy or when there is more potential energy, yeah? Because it's the difference between the two. Yeah? And what nature usually does is trying to get into a balance. So if you have an excess of kinetic energy, then this would try to drive the system into a position of more potential energy. Yeah. So and now, if you now look at two positions and say at this, so we have a state. So the one here, this is the these are two different coordinates. One could also be understood as the energy, and the other one as the velocity, and the other one the position. Okay, it's not written like this here, but in principle. And say we have two states, and that these two states are fixed. So we want to know how it is moving from this state to that state. Yeah, and then this principle basically says, so there are different ways to get there, but the way that we actually take is the one that is the least eccentric. Yeah? So it's, now you could think that when this room is full of air, where we have some potential energy in it, and we have this more or less still air distribution now, and we'll have still air distribution in a minute, then it's pretty unlikely that in between all this potential energy will suddenly turn into kinetic energy, so everything drops down, but we have a very high velocity. Yeah, in principle that's possible, right? But it's extremely unlikely. Yeah, so we'll take a way that is minimizing this eccentricity, you could say. So this is very, very, inaccurate kind of, you could imagine what it does. Yeah. So other than that, it's a physical principle. But maybe somebody can explain it better than me. So now we consider, I mean, in order to see what is the least action, we consider the variation the action. Yeah, so we'll take say this trajectory. So there are two trajectories. Yeah, one is potentially the one that it would be taken, yeah, and the other one could be a small deviation of the one that would actually now be taken. Yeah, like this is drawn like this here. So let me see. So the minimization of this integral is done through the variational principle. So what is variation? Did we have this in mathematics?
I saw it before.
Yeah, you saw it before. Okay. So I always tell the students there are three different ways of writing differentials. Yeah, you know, we had actually, though we have all of them here. No, we don't have all of them here. So this is a partial derivative. Yes. Yeah. And this here, this delta, this we use for variation. And the variation of functional a, so we denote this by delta a, is an infinitesimal but arbitrary derivation from a x I. So this is, we are not, okay, so the difference between this and an actual derivative is that we don't make the, let's say when you take a derivative by x, you make x small, yeah? Here you make you have already a path and you make the difference from this path small. Now you can define this like this. So actually, if you have a variation of a, yeah, so then it will be, yeah, the what is it? The chain rule, yeah. So it's the derivative. It's the derivative of a by all its variables that it depends on, yeah, but at a given position xi, x1 and xn, yeah. So at a given state, but now we are going. So we add a small deviation from this state. Yeah, we take the derivative and then we put this again to 0, and then because it's the chain rule, we multiply this by the variation of dxi. Okay? So now the least action principle is when we take, there is a button on this mouse that does not behave the way I want it to behave. So we take the variation, so we take the variation of this entire action integral and we say this variation is 0. Yeah, then it's the least. I mean, this is 0 is the extremum. When the derivative is 0, then we are in extremum. So this is least action. Okay, and this means we have to do the variation on the Lagrangian and also on this non-conservative force. And now because the Lagrangian is a function of the position, the velocity, and the time. Yeah, we have to take this chain rule. Yeah, so we vary the position, and then we take the derivative of the Lagrangian of the positions, and we vary the velocities. We have to take the derivative on the velocities, and then in principle, we would have to vary the time and take the time but time does not vary. Yeah, so we are not, okay, so we are Newtonian in that sense that time is something that does not vary. That's just going on. So this is why this drops out. But the non-conservative force has to be varied too. So now we have to simplify this thing a little bit. I've written it down here again. We cannot use this directly because we have a problem. There is the variation of the coordinates together with the variation of the velocity of the same coordinate. These two things are not, they are not completely separate. Yeah? The one is the time derivative of the other. Yeah? So then it's kind of difficult to see how we could separate them. So for this reason, we do the following. We do the following step here. Yeah? So we write down exactly the same thing that we have here, and then we add. So this is very sensitive to, I cannot move this without. Sorry. How do I? What was this? Okay, I always need to be online, yeah, in order to run Mathematica here, because I don't have a license on this computer. Yes, so what we do is we add to the above the variation of the coordinates times the time derivative. Now this is how in Mathematica we write the total derivative. Yeah, so this is a partial derivative, this is a total derivative. Yeah, we take the time derivative of the derivative in the velocity on the Lagrangian. So we subtract this, and then we add it again. Okay? So, I mean, we can do this because this is null. Yeah? So, why did we do this? We did this because we want to combine this guy here with this guy here. So, how to combine this? See, this is the coordinate. So, this is the time derivative of the coordinate times the derivative of L by the velocity. Now this, so if this here is the time derivative of this, yeah, and this here is the time derivative of that, right? So now you think the product rule in the opposite way, yeah. So you can actually combine these and take the time derivative out, right? So then you have the time derivative of these two things together. So if you take the product rule of this, you will end up with this plus this, yeah. So now you have separated this, and the advantage that now you have is that what is left here is the variation of the coordinate and no longer the variation of the velocity, meaning you can easily combine these two things here together now. Yeah. So and now you're left with this time derivative here, which you can easily solve because this is under an integral over time. Yeah? So you have an integral over time. So what's of a time derivative? So what you have is you have the the upper position minus the lower position. Yeah? And now there's something important here. We are varying the path going from one position to the other position. Yeah? So the end and the beginning and the end, they are given. Yeah, so there is no variation at the end and at the beginning, right? So this means that here, so when we put this is the end, yeah, so at the end, we know that there is no variation, and in the beginning we know that there is no variation. So these things automatically drop out. So they disappear, and what we are left with is this here. So, and now this can be easily simplified in a few steps. So, and basically all these steps are to do with equating coefficients. Equating coefficients is something very, very important, yeah, to turning big things into small parts. Yeah, we very often use this. So the idea behind this is that we say this is true for all t1 and t2. Yeah? So from the beginning of all times to the end of all times, but also for a single microsecond. Yeah? So if it's this means we can cut the integral as short as we like, and it would always stay true. Yeah? And if this is the case, so if this is 0 for all short, so whatever short integrals ever, then it can only be true if what is under the integral is already 0, right? So this is how we get rid of the integral. Now we want also to get rid of these variations. So there is a little bit a problem here with the stuff that we put here, because this is our engineering assumption that we put that we entered here, yeah, so that some things disappear. Now this here somehow also has to be a function of the generalized coordinates. Yeah, we are not very specific here, but you could, yeah. So, I mean, this is again the chain rule, right? Yeah. So somehow this must depend on the coordinates. So we vary the coordinates and take the derivative of this with the coordinates, and this, I mean, taking the derivative of an energy by path, energy by path, so is a force, because force times a path is the energy, right? So this actually turns out to be a force, and therefore we call it because it was the non-conservative energy, the dissipation. This is what we later call the non-conservative force, and we use to describe this the letter capital Xi, yeah, and these are now, of course, forces for each non-conservative forces for each coordinate. So now everything here depends on the sum of the QK, yeah. Now again, we use the idea of equating coefficients. We say there is a variation, small variation, infinitesimally small, but arbitrary, yeah. Which means that these variations of the different coordinates are all independent of each other. So if the sum is 0, no matter, and the coordinates are independent of each other, so the variation of the coordinates are independent of each other, then this can only be true if all the parts in the sum individually are 0. Yeah? This is equating coefficients. So then we can also get rid of the sum and say, and because delta q, so the variation of qk, is non-zero, but the entire equation is 0, we can also get rid of this variation. And what we are left with is taking all of this out of the equation, yeah, out of the sum, and also dropping this, yeah, because this is non-zero, so the rest needs to be 0. So this is what you are left with, and this is the Euler-Lagrange equation, which looks like this. So we take the Lagrangian, or we take for the Lagrangian the derivative for the coordinates, for one coordinate at a time, yeah, and then we take minus the time derivative of the derivative of the velocity of the same velocity of the Lagrangian, plus, because we are engineers, a dissipation force, yeah, non-conservative force for the same coordinate, right? And this is what we call the Euler-Lagrange equation. And the Euler-Lagrange equation is a very useful way to study mechanical systems in a very straightforward and actually automated way. And this is why we are using this here. Yeah, because I want to show you how now with this principle you can easily set up arbitrarily complex systems. And before we go to arbitrarily complex, we start with the simple. Yeah? Take a simple example and see what this means. So say we have one free mass point. So there's 1 degree of freedom, yeah, in a gravitational field. Say we have a gravitation that is 0, 0 minus g. So in z direction, and there acts a gravitational force, and there's a particle with mass m. And now we have to describe its potential and its kinetic energy. So potential, yes, I mean, kinetic energy is pretty straightforward. Yeah, so it's the velocity squared times the mass, yeah, times 1/2. And of course, we have to write this in the proper coordinates. So it would be, you know, velocity scalar product velocity, yeah, which in Cartesian coordinates is x squared x velocity square plus y velocity square plus z velocity square. The potential energy, of course, depends on what kind of a system you are. I mean, now we are in a gravitational field, so there is a gravitational potential energy. There is, of course, for example, when we talk about molecules staying together, then there is electrical force or atomic forces. They are also potential energies, yeah, but they are potential energies of different kinds. So you can have magnetic potential energy, you can have chemical potential energy, and so on. In a gravitational field, we'll just have, you know, here. I mean, this is also not completely accurate. Yeah, this is, I mean, you know that this is not really how it works, but this is a simplification that you learn in physics, in school usually. Yeah, it's the height times the mass times g is the potential energy. Yeah, so I mean, this is ignoring that Earth is not flat. Yeah. Yeah, so this is, but it is an approximation, it is a sufficient approximation, and we can use this sufficient approximation to get a sufficiently accurate result, yeah, for when we have small, you know, if we are close to the surface of the Earth. So, and then we have our Lagrangian, that is the kinetic energy minus the potential energy, and I have no idea on Earth why they call them T and V, but whatever. So you set this up and now you have your Lagrangian, and now you use the Euler-Lagrange equation to study the dynamics of this. So let's go to the next page and try to do this. So now we have to define our dissipation, which I do here. So we say we have no dissipation. Yeah, we have no dissipation, and then we take the Euler-Lagrange equation. So we have we have three coordinates. We have x, y, and z. Yeah, and it's always important to write here that they depend on t, otherwise it doesn't work. Yeah, so we take the derivative in x of L and in x velocity of L, and take the time derivative and add the non-conservative force. So what we end up with for x is this equation dt mt, the time derivative of x minus m times the acceleration of x in x coordinate is 0. Same thing for y. And the same thing for z, but in z we also have minus gm. So, and then we have this ominous dt. So what this dt is, the dt is the same. Let me see whether I can do this. dt, partial. So now I'm confused. It's the total. Oh, I just recognize I don't know how to write it. Partial derivative, total derivative is not. Okay, I forgot how to write this. This thing here. Let me see. We can. We get this by. Okay, it's dd. Yeah, so I don't know why it's called dd. Yeah, so this is this letter here, and this dd actually is the total derivative. Now we have to understand how the total derivative. I think I have this on the next slide. Now the total derivative in Mathematica, because it's a language, works a little bit different from how we use this in our normal mathematical way. It's similar but not completely identical. So you have to understand what this does. So this ddt, so this is dt. You know, the partial derivative is d, and this is dt. Yeah, and what this does, it is assuming that a is a function of t. Yeah, so that it will take into consideration, for example, that so it will not evaluate this because it does not know in what way a may depend on t. Yeah? Whereas the partial derivative will only evaluate this as being a function of t when you explicitly write that it is a function of t. Otherwise, it will assume that it is not a function of t, and therefore will put this to 0. So now this can be annoying. So I mean the thing that we see here is that it correctly assumed that m could be a function of time. Yeah? So this is kind of annoying for us because we usually assume that m is not a function of time, but it could be. So the way we can write our equation such that it only takes explicit dependencies into account is by writing this with a partial derivative here. But this also means you always have to specify that things depend on time. Yeah, so you always have to specify x as a function of t and x dash as a function of t. Otherwise, this will just put this to 0, please.
Is there a way also to say that a variable is a constant? Or in this case, for example, if we say that the mass is constant,
Yeah, if that the mass is constant.
Then the derivative of time would be 0, right?
You can, I mean, you can explicitly do a substitution of the time of a derivative. I mean, look, you can do the following thing. Yeah, you could say that wait, I have to put this. So say we have this. Yeah. So now what you could do if you believe that. Now this is potentially not nice, but what you could do is that you could say that A is not a function. If you say this is not a function of anything, yeah. So you could say that this. Okay, so this would be a blank. If there is anything, then this you can substitute explicitly with 0. Yeah. So this is something that you could do if you want to tell it that A is not dependent on anything. You can also say it's not dependent on time, yeah. Then, but if you say it's just not dependent on x, then of course it will stay, right? So this is something that you could do. So now. See, what now we did is we'll replace this by the partial derivative, and now we get to these equations here, which you may have written down from your Newtonian mechanics perspective anyway. Yeah. So there's a free particle, so the acceleration in x is 0, the acceleration in y is 0, and the acceleration in z is equal to g. That's what it says, right? So, and now, because they are simple, so we put these three equations into these variables, and now we can actually solve this with dsolve, yeah, because we're using a lot of differential equations here. We'll use dsolve a lot, yeah. So we give these three equations. We have here the dependent variables and we have the independent variable. Yeah? And then we get the solution, and the solution obviously is, because we didn't give any initial conditions, we end up with several constants here. Yeah? So constant, starting constant, and t times other constants. Yeah, and here z is, gt square half. Yeah, it's going downwards. What you expect, right? Okay, so this is a little bit overkill to get something that you know from Newtonian mechanics, but the good thing is now you can do a lot with these things. So the first thing that we want to add here is to see how we deal with constraints. Now, one constraint for a particle could be if we consider a pendulum. Yeah, a pendulum is a particle that are constrained by a string. Yeah. So now the thing that we have to do is we have to think up this constraint in the way of a mathematical function. Yeah. So and the way this could, for example, be done. So it must be a holonomic constraint. So it's not allowed It's allowed to depend on time and on the coordinates, yeah, but it's not allowed to depend on the velocity. So such a constraint now could be that x of t is a starting position x0 plus the length of the string times sine of alpha t, and z would be z0 minus L times the cosine of alpha t, right? And say y would simply be a constant, yeah? So it's constrained in this plane. So we can see, we can use some Mathematica fun for see whether this actually makes sense. So there in Mathematica we can manipulate objects. So this is something that gives us here some way of manipulators, yeah. And we have to use modules. This is something that I will explain a lot later. Modules give us a module defines a scope. Yeah. So you are familiar with C++, so you are familiar with what a scope is, right? No, you are not familiar with what a scope is. Okay, if I explain what a scope is. So okay, let's say you have a for loop, and in the for loop you write int I, yeah. So then this variable I, or whatever variable you have in this for loop, will be local to this loop, right? Because it's defined in this loop. And the way in C++ you do this, you have these curl brackets, yeah. So whenever you put curl brackets, so in a loop you do this, maybe without thinking about this, but you can do this anywhere in the code. So you define a scope with these brackets, and everything that you define inside this will only be valid inside this. So this is important. In particular, say if you have something recursive or so. So if you want to if another variable with the same name appears somewhere else, yeah. So it's important that here we use our local definition, yeah. So now and in particular in Mathematica this is important because if you don't do this, so you will always you run out of variables very quickly, yeah. So this function, this is not a function. This is not a function. So we have locals. We specify the local variables here. So local is only what we specify here in the beginning in this list. This is how it works. Actually, we can. Okay, so this is potentially not the most efficient way. I've written this down because you can initialize these variables also. Inside here, yeah, while you write them here, but I initialize them later, yeah. So now these variables are now local to this module, yeah. And now we display this. So okay, we define x and z in the way that we have it here. Then we show parametric plots with some graphics points and so on. Now this is not so important. The thing is we have here specified this beta, and we substitute this beta by the alpha, and the alpha is the thing that we vary in the manipulate. Okay. Yeah. So now we have here an alpha, and I can change this alpha from 0 to 2 pi to see that this is the complete range. Yeah, so just for me to see whether I made a reasonable constraint. Okay? So now let's take this constraint into our Lagrangian. Yeah? So we okay, let me just briefly, yeah? So I made a list of constraints. Yeah? So I'll take as replacements. Yeah? I take the Lagrangian and simply substitute the constraints. Yeah? So, and what we see is that z is substituted, but x dash, so the derivative, the velocity is not substituted. And the reason here is that Mathematica is either not intelligent enough or they didn't want to do it that way, I don't know, but it's not doing this because it's only substituting things that it can directly identify. And sometimes this is a little bit strange because they are also distinguishing between minus x and so this is I don't actually, yeah, so sometimes it does not see that there is something in it, yeah. So it does not, when it sees y dash, it will not replace y dash with the derivative of. So if you want to do this, you have to help it and to do it a little bit by hand. And for this, again, we have to understand eager and lazy stuff. Yeah. So problem is that that this derivative function, yeah, this is an eager function. So if it can take the derivative, it will take the derivative. Yeah. So if we want to do this replacement, we have to. I mean, there may be other options to do this, but this is at least one of the options, is to stop the eagerness of this function. And we in Mathematica, we can stop the eagerness by the function hold. So, okay, this is what is to do, but don't do it. Okay? So we hold. We do this replacement here. Now we take some function with this underscore, and this underscore is a pattern. Yeah. So some function will take any function like x, so any function that has taken already the derivative. Yeah. So the problem is it does not. I mean, it interprets as having taken the derivative already. You understand? So dx is take the derivative, and then x dash is have taken the derivative. Yeah. So now some function where you have taken the derivative, hold this function and take the derivative again. Yeah, but hold the derivative and then do the replacements. Yeah, and then when you did the replacements, then release the hold. Yeah?
So that means that this is going to be done. Well,
the question is the order. So if you don't hold it, then it will immediately take the derivative here, and you have not done anything. Yeah? Then so if you hold this here, then the next thing it will do is doing these replacements, and after it's taken the replacements, it releases the hold, and then it will evaluate the derivative. Yeah?
Okay.
So, I mean, this is a lot of Mathematica programming is you specifying the order in which operations take place.
Okay.
Yeah? So, and this is what we did here. Yeah? And it depends really. So this is something that you need to understand. In what order commands are executed. So now, see, now everything is beautiful. So we got the z replaced, and we get the x and the y replaced. The y actually disappeared. Yeah, because it's a constant. Yeah. So now everything here depends on alpha and alpha dash. Yeah? Alpha is the time derivative of the angle. Yeah? Alpha dash is the time derivative of the angle. So now we also have to get a force for alpha now, and we set this to 0. And now we can set up a differential equation for the coordinate alpha. Yeah? I mean, we started completely from Cartesian coordinates. We set our constraints, and then we get a differential equation for alpha. Yeah?
Yes.
So this equation here we can also further simplify, because with some assumptions. So for example, it will not divide. You see, there's m on both sides. Yeah, you know, in the equation of pendulum there are m on both sides. Yeah, so it will not simplify this away because m could be 0. Yeah, so now we have to specify m is larger than 0 and also L is larger than 0, and then it covers it. It sees that we can divide by m and by L, and so we can simplify this to g sine alpha plus L, the second derivative of alpha is equal to 0, right? So now we derived this equation. How's time? Yeah, and now we can solve this. Now we take the analytical solution, and as you may know, the pendulum, the real pendulum, not the mathematical pendulum, has no analytical solution, and this is due to the sign here. Yeah. So now what we do in second semester lecture is then saying, okay, we take a series expansion of alpha, and then sine alpha is alpha, and then everything is nice. Yeah, but in principle, this is what comes out, and the solution would be a little bit different. Now, so you cannot solve this thing here with an analytical solution, but what you can also do in Mathematica is you can ask it for a numerical solution, and this is done by ND solve. So if we use ND solve, we have to do a little bit. So this is now a numerical solution, meaning we don't get an algebraic answer, and if we don't get an algebraic answer, we have to be specific. Yeah. So you remember when we solved the other equation, we didn't need to be specific. Yeah. So there were constants coming out. Yeah. So now we need to be specific. So I have to set initial conditions, two initial conditions, alpha at 0 and alpha dash, the velocity, the angular velocity, at the time 0. And I have to specify all parameters numerically. So say that G is 9.81 and L is equal to 1, say. Yeah? And then also I have to specify the interval from 0 to 20. Okay, then I have this numerical solution, and this numerical solution, so I can now evaluate this alpha t with the numerical solution, and I do this from t, I mean, in the range where I solved this, from 0 to 20. Yeah, I mean, I can do something stupid here. I can also over-evaluate this. It's always funny to see this. So I don't know why they are doing this, but they use an interpolation function. Yeah, and this interpolation function, I mean, for the solution, and this interpolation function can be evaluated outside its definition. So it will, if you do this, it will extrapolate the solution. Yeah. So here you see it's trying for what in a strange way it will extrapolate the solution. So you have to. It's your own responsibility to only evaluate it in the range where you actually got the solution from. Yeah. Okay, and now you can also put some labels in here. Yeah, so they are a little small, alpha and t in seconds. Okay, Now you see, we can, starting from this principle and Cartesian coordinates, we can also get, for example, to this pendulum equation. Yeah. So, okay, now, yes, you can animate this thing using animate, again, module, this is local variable, and this is, this is similar to manipulate, yeah? Here again, you could have the idea that we run this further. Let me see what is happening. Now it will take the extrapolated solution. Yeah, so it will potentially, I don't know what is, it will, okay, we saw that it is going to explode, right? Let us see, it will now get to zip, zip. Okay, it doesn't like it, yeah? Don't do this. Okay. So, right. Now, we talked about constraints. Now let's talk about non-conservative forces. Yeah, this is a little bit kind of, yes, I mean, this is dissipation. I mean, you can't say that dissipation is not physical, but dissipation is something that happens on the macroscopic level. Yeah, microscopically it's just different degrees of freedom behave in a different way, and if you don't look at this degrees of freedom in particular, you see dissipation. Yeah, so things that you would consider to go into heat. So say you want to add friction in the air to this pendulum. Yeah, I mean, if I give you this. You have this equation in alpha, and I ask you now to add friction in the air. And suppose I did this last semester, and you have no idea about this methodology, then you would certainly have some troubles and getting this into this equation, I guess. Maybe you don't. Yeah, I just assume. So because what is, I mean, the friction, describing friction in air with the angular velocity is not absolutely straightforward, I would assume, right? In Cartesian coordinates, you can actually, I mean, you may know that there is some usually we describe this by a friction coefficient CD and the lift coefficient CL, yeah, and you may know that the force that is acting on the particle is proportional to the velocity squared, yeah. But it's not the scalar product of the velocity, because the force has a direction. So it's actually velocity times minus velocity, yeah, in the opposite direction, minus velocity times the magnitude of the velocity. Yeah. So, and this times surface area, mass of air, and 1/2, some things that you could consider to be constant. Yeah, I mean, it depends on the area and the shape of this. But say we put all area, shape, mass of particles, we put all of this into a single constant that I now call here Ca. Yeah, and I have this going. The force is acting in the opposite direction to the velocity of the thing. And this here is the Cartesian magnitude, the magnitude of the Cartesian velocity, right? And this here is the velocity is the velocity itself. So this is now going to be velocity square. So the Vx is the velocity of the air, yeah, because it is the velocity relative to the air, yeah, and this here, this Cx dash is the velocity of the particle in a laboratory frame of reference. So this is why we have to subtract the velocity of the air everywhere. And we do this for x, y, and z. So now we want to get this into our alpha coordinate systems, yeah, into our alpha coordinate system, and this we do. So we need to have C alpha. We take all of our forces. We replace in the so we have again, we have again to turn this into x, otherwise we cannot do the replacement. Yeah, so we do what we just learned. Yeah, we hold this and then we replace the x, y, and z with our constraint. And what drops out is the force in alpha. Yeah. So we now have the force in alpha. Yeah. So now we simply apply our Euler-Lagrange equation again. So we assume the air is not moving. Yeah. And now we get to this. Now we have this equation of motion. Which, yeah, so here is something related to, this is what we had before, right? And this strange thing here, this is the track in terms of alpha, yeah? So simply let Mathematica do it, yeah? And then we take the numerical solution. So of course we have to specify everything. In particular, we have to specify this CA. We also have to specify M, because you see that in this context there is no M in this, there's no mass in the friction. Therefore we cannot divide by M. Yeah. So obviously if you have once you have friction, so without friction, the mass doesn't count. Yeah? So you drop something on the moon, everything drops the same way. Now, once there is friction, then obviously the mass changes the behavior. Yeah? So this is what we observe here. Yeah? So therefore you have to specify the mass. So, and then, so you can evaluate, run this, and see this behavior here. So you get, you get some decay, but once it gets low, yeah, the friction becomes smaller, and you see for a long time it will just do a little bit of movement. Okay, so just example, everything clear, right? So, yes, just other example, you can specify a velocity here. No? So, you can add wind. So now I put this to 1, because everything was in meters per second. What's it called, the SI units, yeah, so this would imply this is 1 meter per second. Can put here a larger number. Now we have to solve this again, I guess I have to solve it again. And when I solve it again, you see now there's a strong wind blowing, and now the thing is like something. I mean, I could potentially, because I'm wondering whether this is dependent on where it started from. Let's have the wind in the opposite direction. Okay. Not so much different. Yeah, so you can, I change this back to what it originally was. Yeah, this is the thing with wind. It will potentially okay. Not so interesting. Now I guess the big advantage of this principle is its ability to very straightforwardly deal with large systems. Yeah? And even though we are now using only one body, so next week we'll talk about many bodies. Yeah? The nice thing with this is you simply have all your energies. Yeah? You put all your energies in a box, and out comes the equations of motion. Yeah? So simply put all energy in one box. So now let's say going one step further and taking a system with 3 degrees of freedom, or actually 2, but yeah, a pendulum that is not constrained to a plane, but a pendulum that could be floating in 2 different ways. So now there is a question how you define this, and I'm showing this as an example that because we are in the beginning of this lecture series, I could say I do it the stupid way first. Okay? So say you have a pendulum on a string, and you want to put this into a constraint. So what you could say is that there is a place where your pendulum is attached, and then there is the actual mass of the pendulum somewhere, which is your particle. And what the string does, it is constraining the distance between these 2 points, right? So now you can use the Pythagorean theorem, yeah, to calculate the distance between these 2 points and say this is a constant L. Yeah? So then we have to choose. So this is one constraint. Yeah? So we have one particle and we have one constraint. So we get 2 equations of motion. Now we have to decide what equation of motion we want to have, because we have possibilities. Yeah? And one kind of a little bit stupid possibility, so we have to remove one of the coordinates, and let's say we remove z. Yeah? So what we do is we define constraint applied to z by solving the constraint for z. And see what is z? Well, now you see this is a quadratic equation with, so obviously we get 2 solutions. Yeah? One negative and one positive. And if you don't know what these are, we can actually plot them, and what you see is, very obviously we have the lower shell and the upper shell. Yeah? Now, defining your coordinate system like this is not a good idea. We'll do it anyway. Yeah, because your constraint would do one thing in the one world and another thing in the other world. The problem is if we consider as our coordinates only x and y. And for each x and y, obviously there can be two positions for z. Yeah? So this is not a clever way to describe your system. But anyway, we are free to do this. Yeah? So what we are going to do is we take the Lagrangian now in 3D. We take the Lagrangian, again we replace all the derivatives and replace every occurrence of z. Yeah? So now we get our Lagrangian like this. So velocity in x and velocity in y are still there, but x, okay, so x was not there in the first place because there was no. So this is basically this here is the potential energy, right? So in the potential energy, z gets replaced by this, and in the kinetic energy, z dash gets replaced by this. Yeah, everything automatic. So. Now we also want to have the friction in the air. So how do we do this? Very simple. We'll take the xx, yeah, that we have defined already, and in this we will replace the z with its constraint. Yeah. So we'll take, by the way, we take the first. Maybe I've not said this. So we take the first constraints, yeah, so that we get only one of them. Yeah, so this is the first. We take the lower shell. Yeah, so this is the first solution, the first replacement. So if I write the 2 here, will be in the upper part, which will give us a problem because the pendulum would try to go down, and then it will hit the boundary where it's no longer in its range of, that will give us a problem. Okay, now you see we get now this force only in terms of x and y. Yeah? So, and now we can set up new partial differential equations, ODEs, yeah, for x. So we take the Lagrangian in 3D. We do this for x. Okay, we specify velocity, yeah. We do this for y, and then we get these partial differential equations. Ordinary differential equations. I mean, beauty is something else, but we have the computer algebra system that does this for us, right? So, and then, we are already at the end of the lecture. So then we specify initial conditions. We specify our parameters, and then we solve for 20 seconds, and then we can animate this. Yeah. So, and here, for example, x, we can have, I don't know, for example, we could have a strong wind here. Let's see what this does. Does this do anything? Okay, this was a little, okay. So it runs out of the domain, right? I mean, it's overshooting, yeah. Therefore, this didn't didn't work. So now I've put, wait, no, I made a mistake, sorry. This is, okay, so this is the initial condition, sorry. This is not the velocity of the air, this is the initial condition. Apparently, okay, I cannot change this because we have already set it to 0 here. So I would have to change this here, say, and then I would run this again, and run this again. See whether this is. Okay, now we see the wind, yeah, blowing. Okay, I'm going to remove this, otherwise I can't use this the next time. So okay, putting the wind away now gives us again this solution, this boring solution. Okay. Yes, so this is kind of what I had today. We are going to study more particles next time, and also more realistic potential energies. Yeah. Any questions? Should I stop the recording? I mean, I stopped the recording first.